You know, we feel hot and cold every single day, right? But behind those really simple feelings, there's some seriously fundamental physics at play. Today, we're going to pull back the curtain on the science that runs everything from your morning coffee to the entire universe. So, yeah, let's dive in.
So, let's start with a really simple question. You stick a thermometer in a cup of hot coffee, and a few seconds later, boom, it gives you a number. But how? How does it know? What is actually happening between the coffee and that little glass tube?
The answer is actually so much cooler and more profound than you might think. And to really get it, we've got to lay a little groundwork first. We have to get crystal clear on what we even mean when we say words like temperature and heat.
All right, first things first. We have to separate two ideas that we totally mash together in everyday conversation: temperature and heat. Turns out, in the world of physics, they are worlds apart. Okay, so this chart breaks it down perfectly. Over on the left, we've got temperature. Think of it as a property of something. It's basically a measure of how much the molecules inside an object are jiggling around. It's their average kinetic energy. But heat, over on the right, that's not something an object has. Heat is energy on the move. It's the flow of that energy, and it only happens when there's a temperature difference.
So let's get super specific here. In science, temperature has what's called an operational definition. That's just a fancy way of saying we define it by how we measure it. So, scientifically speaking, temperature is quite literally the thing a thermometer measures. It's like taking a snapshot of the average energy of all those jiggling molecules.
And heat transfer, well, that's the action. It's the process, the actual movement of energy from a hotter spot to a colder spot. So here's the bottom line, and this is important. Objects don't contain heat, they contain internal energy. Heat is just the name we give to the transfer of that energy.
Okay, so if energy is flowing, that naturally leads to the next question. What happens when it stops? This brings us to a super important concept: thermal equilibrium.
Just think about it. You drop a cold spoon into a piping hot bowl of soup. We all know what happens, right? Energy flows from that hot soup into the cold spoon, and the spoon starts to warm up. But it doesn't just keep getting hotter and hotter forever. At some point, things just settle. So what's really going on in that moment of stillness?
And that point, that moment of balance, that's what scientists call thermal equilibrium. It's the state where there's no more net flow of energy between the two objects. The great energy exchange has finally balanced out.
And this is the absolute key, you guys. This is the big takeaway. When two objects have reached that perfect balance, when they're in thermal equilibrium, we can say definitively that they have the exact same temperature. This one idea is the secret to everything.
This idea is so important, so fundamental to how the universe works, it actually gets its own law. It's called the zeroth law of thermodynamics.
And get this, there's a pretty funny story behind the name. Why zeroth? Well, by the time physicists really wrote this rule down in the 1930s, the first and second laws of thermodynamics were already famous. But they realized this new law was actually more basic, more fundamental than either of them. So what comes before one? Zero. And so the zeroth law was born.
So what is this law? Well, it's actually just plain, simple logic. It goes like this. If object A is in thermal equilibrium with object B, and that same object B is also in equilibrium with a third object, C, then it has to be true that object A and object C are also in equilibrium with each other. It sounds simple, almost obvious, but the implications are huge.
Okay, deep breath. We've got all the pieces now. Temperature, heat, thermal equilibrium, and the zeroth law. So let's put it all together and finally answer that question about the coffee.
You ready for this? It's kind of a mind bender. The big reveal is this. A thermometer doesn't measure the temperature of the coffee. A thermometer measures its own temperature. Just let that sink in for a second.
So what on earth does that mean? Let's break it down step by step. You take your thermometer, let's call it object A, and you put it in your coffee, object C. Right away, energy flows from the hot coffee into the colder thermometer. That flow continues until they reach that magic balance point, thermal equilibrium. At that exact moment, the thermometer now has the same temperature as the coffee, so the number you read on the thermometer, that's the temperature of the thermometer itself, which, thanks to the laws of physics, is now also the temperature of the coffee. And it's the zeroth law that guarantees this whole thing works every single time. So the main thing to remember is this. The thermometer isn't some magical probe that scans the coffee from a distance. Nope. It actually becomes part of the coffee thermometer system. It has to reach a balance with the coffee, and only then can it report on their shared temperature. It doesn't just inspect the coffee, it joins it.
Isn't that wild? This one simple, kind of weirdly named law is the reason we can trust any thermometer anywhere. It's just a beautiful example of a deep, profound physical truth hiding in plain sight, in something we do every day. And it really makes you wonder, if the 0th law is this cool, what other secrets about the universe are the 1st, 2nd, and 3rd laws waiting to tell us?